In this goal, we're going to be talking about spontaneous reactions. A spontaneous reaction is one in that as soon as the activation energy is supplied, the reaction will proceed without no outside help. To have spontaneous reactions, generally they lose heat and they have an increase in disorder. But that's not always the case. You can still have a spontaneous endothermic reaction, and you can still have a decrease in disorder and still have it spontaneous. But in those cases, temperature is important. And we're going to talk about all this in this goal. So let's first look at our cartoon. Pushed to the max by the algebra test, Tim's brain spontaneously combusted. So the activation energy there is, let's look at the right-hand side. So we have some beads that are separated. They're very orderly. When you shake the container, they get all jumbled up. What are the possibilities that you could shake that second container to look like the first one? And the answer is that would not be a spontaneous process to get them all lined up like that. You would have to open up the container and rearrange each of them. Let's look at something that is called free energy. Free energy was studied by a scientist whose last name was Gibbs. So this is also known as Gibbs free energy and is given the symbol G, or delta G, the change in free energy. The free energy is the driving force of a reaction. From knowing the value of our delta G, we can determine if it's spontaneous or non-spontaneous. And if you look at the equation right here is just like the other equations we've looked at. You take the sum of the products and you subtract the sum of the reactants. And you can find these values on the table that should have been included in your homework. And if you can't find it in your homework packet, then you can also look on Canvas and it should be there, that you can print it out and look up those values. If you have a negative value of delta G, then you have a spontaneous process. If the experiment occurs in the lab, then that would be spontaneous because it worked. If it didn't work, then you know you would have a non-spontaneous process. So a good example of this is if you wanted to make ice cubes, you could fill up your ice cube tray. If you just put them on the kitchen counter, would they turn into ice? And the answer is no, unless your house was really, really cold and you lived in a really cold climate and there was no heat in your house. So this would be a non-spontaneous process of making ice cubes on your kitchen counter. However, if you were to put that ice cube tray into the freezer, then now this process would be spontaneous. So sometimes in spontaneous processes, temperature is important. Now there's another equation that has delta G in it, and this is the equation that combines entropy and enthalpy, and also temperature. And it is called the Gibbs free energy equation. It looks like this: delta G equals delta H minus T delta S. And it's very, very important that temperature is in Kelvin. Where we're looking at these signs being positive or negative, we don't want to mess up our equation by adding in like a negative value of degrees Celsius. So we need to be in Kelvin so that we always have a positive number. The values that are found on that chart that has your delta G, your delta H, and delta S, these are all at standard conditions. So room temperature, which is 25 degrees Celsius, or 298 Kelvin, and 1 atmospheric pressure, or 101.3 kilopascals. Let's go ahead and do a problem using the Gibbs free energy equation, which is right here. So delta G equals delta H minus T delta S. And let's identify what we have in our equation. If the change in enthalpy is, so this is our delta H, and the change in entropy, so this is our delta S, will the reaction be spontaneous at this temperature? So there's our temperature. So let's go ahead and plug it into our equation. So this is setting up our equation. Notice, however, that our S is in joules. So you need to watch out for this. So we need to convert this to kilojoules by dividing by 1,000. So that would be 0.020. And let's go ahead and solve this problem now that we're all in kilojoules. Now it's assumed that we have just 1 molar amounts of the substances. So this would be a negative 289 kilojoules per mole. And so the question says, will it be spontaneous? And the answer is yes. And you know it will be spontaneous because that delta G is negative. So again, a negative delta G tells you that it's a spontaneous process. It will work at this temperature. Now, if you notice in the Gibbs free energy equation, you could also solve for delta H, Or you could solve for delta S, or you could solve for temperature, given all the other values. So here's a problem where we are solving for delta S. We can rearrange our equation to be right here. So delta S is equal to delta H minus delta G over temperature. And we can look up our values on our little chart, and I put them here. And we can calculate what the delta S is. So let's go ahead and do that. So delta S is equal to, we do need to convert our temperature from 25 degrees Celsius. So remember, Kelvin is always bigger than degrees Celsius. So we're going to take 273 and add 25 to that number. So our Kelvin in this case is 298. This is our standard temperature that we're just using in here. And when we work this all out, we get a positive 2.70 kilojoules per Kelvin. And it's actually, there's a mole there too. So that is our entropy for our problem. What does this tell us? So this is telling us our disorder is increasing. And we can also answer number 2. Is the reaction spontaneous? So we need to go up to what our value of G is, and we see that our G is a negative 452.4. So is it spontaneous? Yes, we know because it's negative. And then the last question, is it exothermic or endothermic? And so we go up to our H, and we see it's negative, so that means it's exothermic. How do I know? Because our value is negative. So this is increasing disorder because our value is positive. We were able to calculate it. And it's spontaneous because delta G is negative. And it's exothermic because our delta G is negative. Or delta H is negative, excuse me. All right, so to review, enthalpy can be figured out through experimentation, through products minus reactants, through this Gibbs free energy equation, and also in the next goal we're going to be looking at Hess's law. So those are 4 different ways that we can calculate enthalpy. And remember, enthalpy is delta H. For entropy or disorder, which is delta S, it can be calculated through products minus reactants and also using Gibbs free energy equation and solving for that delta S. And then Gibbs free energy can be figured out by products minus reactants and also Gibbs free energy equation, and it has a symbol delta G. So what do all these values mean? So if I have a negative delta G, this means it's spontaneous. So a positive delta G would be non-spontaneous. What does a negative delta H mean? A negative delta H means that it's exothermic. What's a positive delta H? Then that is endothermic. And last but not least, we have a positive delta S. So this one is entropy, or it means an increase in disorder. And we have a negative delta S. This is a decrease in disorder. Now, of all these values, what does nature tend to follow? It tends to follow spontaneous, exothermic, and an increase in disorder. Most of our chemical reactions in the lab, they follow these 3 things. Could you have other combinations? Yes, you can, but these are the most common. So there's a little chart here to help you figure out if something is spontaneous or non-spontaneous based on the entropy and the enthalpy. So let's first look at our chart. So I put exothermic here, and I put our increased disorder here. So these are the ones that nature favors. And so if a chemical reaction has both of these, it's both exothermic and increasing disorder, it will always be spontaneous. Well, what happens if you have the opposite? If you have an endothermic reaction or you have a decrease in disorder? In this combination, this will be never spontaneous. Well, what if you have one but not the other? So maybe it's exothermic and a decrease in disorder. So this one will be spontaneous if the temperature is low. And I've arranged it in this grid so that this is in the lower box. So it will be spontaneous if the temperature is low. If you have an endothermic reaction and an increase in disorder, this one will be spontaneous if the temperature is high. Okay. Let me give you a good example of an endothermic reaction that is increasing in disorder. When I go to boil water, water is a liquid, and I'm going to take it to be a gas. So looking at this, you can see that your delta S is positive. And that is because you're going from a liquid to a gas. But I have to add heat to make this happen. So when I add heat, I can boil that water and it is a spontaneous process. But I do have to have a higher temperature. I can't just boil water at room temperature. Okay. And then another example of this other one right here. This is a good example of this is making ice cubes, and I'll put it up here. So when you make ice cubes, you're going from liquid water to solid water. Well, you're not just going to make ice cubes on your kitchen counter in the ice cube tray. What do you have to do? You have to remove the heat. And how you remove the heat is by putting it into the freezer. So when you remove, remember Le Chatelier's principle. So if I remove the heat and that leaves, it's going to favor the product side. We are decreasing our disorder, but it is still an exothermic process because we're removing the heat from that liquid water. You can always try to figure out if it's spontaneous or not. So if you didn't want to memorize the chart, which I highly recommend, you can plug in some fake numbers just to see what would happen. So if you have, in this first case, you have a exothermic reaction, so you have a negative delta H, and you have a positive delta S. When you go and plug in some numbers, and I'm just going to put like a negative 50 here, and my temperature, so because you're subtracting this whole little group, I'm going to just keep my temperature really low and just see what happens. Notice that if this one is positive, and of course that one's always going to be positive, anytime you multiply a positive number by a negative, you're going to get a negative. So that's your only choice here, is because you're multiplying these positive numbers by a negative, you're always going to get a negative. Let's look at the never spontaneous. So I'm just going to pick a plus 50 here for my enthalpy. And then let's look at here, we're subtracting. My temperature is always going to be positive. And if we are decreasing disorder, so then my delta S is a negative. Notice that I have a negative and I'm multiplying it by a negative. So this is always going to, and so I'm going to end up with a positive number here. And this one's already positive. So I have no choice here. This is always going to be positive. So that is why if you have an exothermic reaction and your delta S is positive, it's always going to be a negative number when you use that Gibbs free energy equation. And down here at the bottom, if you have an endothermic reaction and a decrease in disorder, then you're always going to get a positive number. So it will be non-spontaneous. So having a low temperature and high temperature, it just kind of depends on the problem, but the temperature will determine if it is spontaneous or not. So I'm just going to put in some fake numbers so we can go through them. So let's say we have an exothermic reaction, and let's see, so this is subtract the temperature, so I'm going to have a low temperature of 3, and I'm going to have a decrease in disorder. So you can see here that this is going to end up being a positive 30. So as long as my temperature is low, it will still be negative. Okay, let's see what happens if I raise the temperature. So I'm just going to raise it to 10. So I'm going to get a positive 100. So now I'm going to get a non-spontaneous because it's positive. So you can kind of work it out and see that as long as the temperature is kept low, then it will stay spontaneous. It'll stay negative. Let's look at the opposite situation. If we have an endothermic reaction, so I just put positive 50. Let's see what happens with a low temperature. We end up having, this is a minus 30. And so we still end up with a positive number. So this will be non-spontaneous with that low temperature. But let's see what happens if we raise the temperature. And again, it always has to do with that negative sign in the equation. And let's go ahead and take it up to 10 for the temperature. So I end up with a minus 100. And so I end up with a negative number when I add those up. So again, high temperature would be spontaneous.